So why does SOS use hydrogen? So if you've been watching recently and seeing all the leaks and you think, well, why didn't they use methane or why didn't they use RP1? So today we're just going to have a little chat about why you might choose one fuel or the other. Now, you may be aware that the Apollo era Saturn V, certainly for its first stage, and that Falcon 9 of Falcon Heavy uses RP1. In the case of the Falcon 9 and Heavy, they only use RP1. RP1 stands for Rocket Propellant 1, and it's a form of highly refined kerosene that just gives sort of ideal burn characteristics for rocket engines. Other rockets, such as the SOS, as we've just mentioned, the Delta IV Heavy, and the Long March 5, which is China's moderate heavy lift vehicle, they use hydrogen for some of the stages, or in the case of the Delta IV Heavy, for all the stages. Now, the one that's getting all the attention at the moment is Starship, and to an extent New Glenn, Blue Origin's New Glenn, and they're both designed to use methane as propellant. In the case of Starship, it's the Raptor and Raptor 2 engine, whereas in the New Glenn, it's the B4 engines. So the question is, why would I use one or the other? And the answer is, it depends on what you want to design. So you have to look at a whole bunch of things: cost, ease of use, if you think of the SOS, hydrogen problems, efficiency, reusability, thrust, in situ fuel production. So today we want to consider just one aspect, and that's Newton's laws and something called momentum. Now, for you those who remember being back at school and doing physics, Newton had three key laws, and for massive things, what we call macro physics, Newton's laws are king. Now, when we get to the very, very infinitesimally small, we end up with quantum physics, which is completely different. At least, there is perhaps a greater equation or greater understanding which covers everything, but in the large things, it simplifies to Newton's laws, and in the very, very small, it simplifies to quantum physics. Now, Newton basically said that the resultant force, and we say resultant because that means you could have more than one force acting at a time, but if you summed them all together in terms of how big they were, its magnitude and the direction, you could come up with one individual force acting in one individual direction. And this force on an object is equal to the rate of change of momentum. Now, that might not help you very much. You might think, well, what does that mean? Well, what is momentum? And the answer is very simple. It's the product of an object's mass and velocity. And when we say product, we're saying take the mass of something and multiply its velocity. So let's just give an example here. If a rocket ship has a mass of 100 kilograms, and this is a very small rocket ship, and it's moving at 5 meters per second, then this rocket ship has a momentum of 500 kilogram meters per second. Now this becomes important. Why? When we add Newton's third law, and what Newton said is, for every action or force in nature, there's an equal and opposite reaction. I push the floor pushes me. So if an object A pushes B with a force, let's say, of 10 newtons, then object B will push object A with a force of 10 newtons in the opposite direction. So push B, B pushes A back. Now this leads to a very, very important idea. And if you put them together, and we recognize that equal and opposite forces are acting for the same amount of time, they will cause equal and opposite changes in momentum. And this is the idea of conservation of momentum. So if rocket ship A is being pushed to the right, or the hot rocket exhaust for 1 second is expelled at a certain velocity, let's say to the left, the product of mass and change in velocity will equal also the change in momentum of the rocket in the other direction. And this becomes very important for two key reasons. And the two things are efficiency and thrust. Now, efficiency is effectively saying how much change in momentum do I get for a certain amount of fuel. And that is largely based on exhaust velocity. And the clear winner for exhaust velocity is hydrogen. Hydrogen is the smallest molecule known to mankind, the smallest molecule that we know in the universe. Not talking about subatomic things. And for that reason, you can accelerate it to a much greater speed. Also, it's to do with the amount of energy it releases for a certain amount of mass. So hydrogen is the clear winner in efficiency. And we're going to learn later why we tend to use this in upper stages. You think of the Centaur rocket, which is used in a lot of ULA's upper stages, and it's going to be used effectively, or a simplified or a slightly changed version that's going to be used for the SLS. But that's not the only story. The other story is thrust. Thrust is telling me how big of a force that I'm having it for any given time. And though that's partly based on velocity, it is largely based on how much mass flows through the engine at any time. And the clear winner is RP1. Why? For one amount of liquid, say 1 liter, it has a much greater density, it has that much more mass. So for a flow rate, and we're talking about so much volume going through an engine, and the size of the engine, basically you'll have almost the same flow rate going through a hydrogen engine, a methane, or through an RP1 engine. We just have so much more mass flow rate with RP1, meaning that though it has a lower velocity, or exhaust velocity, it has a much greater thrust. This allows us to recognize that, for instance, on the Saturn V, its first stage, which actually has to fight against gravity, that literally has to take that rocket and get it out into, well, not quite outer space, but above the Earth's atmosphere, and then get it turning and actually accelerating horizontally. RP1 is very effective. It also tells us why things such as the SLS cannot use hydrogen alone. It just does not have the thrust. It doesn't have the force to push or to act against the gravitational field or gravitational forces acting on the rocket. Hence, it uses solid rocket boosters, and it needs that initially. Now, this is just the beginning of what we want to talk about. To understand efficiency and thrust, we need to talk about the ideal rocket equation. We also need to realize that the mass of a rocket is constantly changing as you use thrust and as you use fuel. So our next video, we want to apply the ideal rocket equation. We want to look at 3 different engines: a methane engine, an RP1 engine, and a hydrogen engine, and help us to see why, for instance, that the Raptor engine has been designed to use methane. I hope you find this interesting. It's looking at a simple way, looking at basic physics in a very simple and understandable way, and to apply to aerospace.